welcome to this problem walkthrough. Today, we'll be exploring problem number 25, titled Reverse Nodes in K-Group. This is a fascinating and challenging problem that tests your understanding of linked list manipulations and algorithmic thinking. Let's dive in and uncover the optimal solution step by step. In this problem, we are tasked with reversing the nodes of a linked list in groups of K. The goal is to modify the linked list such that every consecutive group of K nodes is reversed. If the number of nodes in the list is not a perfect multiple of K, the remaining nodes at the end of the list are left unchanged. It's important to note that we can only change the links between nodes, not the values within the nodes themselves. For the input, we have two components, the head of the linked list, which serves as the starting point of the list, and the integer K, which defines the size of the groups to reverse. The output will be the head of the newly modified linked list after the groups have been processed. Let's look at the first example. Here, the input linked list is 1, 2, 3, 4, 5, and K is set to 2. This means we need to reverse the nodes in groups of 2. First, we split the list into groups of size 2, 1, 2, 3, 4, and 5. The first two groups, 1, 2, and 3, 4, are reversed to become 2, 1, and 4, 3, respectively. The last group, 5, remains as is because its size is less than K. Combining these groups gives the final result, 2, 1, 4, 3, 5. This example demonstrates how we process groups of K nodes and leave smaller groups untouched. Now, let's examine another example with a larger input list. Here, the linked list is 1, 2, 3, 4, 5, 6, 7, 8, and K is set to 3. The list is divided into groups of 3 nodes each, 1, 2, 3, 4, 5, 6, and 7, 8. The first two groups, 1, 2, 3, and 4, 5, 6, are reversed to become 3, 2, 1, and 6, 5, 4. The last group, 7, 8, remains as is because its size is less than K. Combining all the groups results in the modified list, 3, 2, 1, 6, 5, 4, 7, 8. This illustrates how the approach handles larger lists and ensures smaller trailing groups are not reversed. In the third example, the input list is 1 and K is set to 1. Since K equals 1, we do not reverse any nodes, as reversing a single node has no effect. The list remains unchanged, and the output is simply 1. This example highlights that when K is 1, the problem reduces to returning the original list as is. It's a simple edge case to verify. Finally, let's discuss some constraints and edge cases. The number of nodes in the list can range from 1 to 10,000, and the value of each node lies between 0 and 1,000. Additionally, K must be at least 1 and cannot exceed the number of nodes in the list. For edge cases, if the list contains fewer than K nodes, no reversal takes place. Similarly, if K equals 1, the linked list remains unchanged. If the list size matches K exactly, the entire list is reversed as one group. Even if all nodes have the same value, the reversal must still occur based on their positions, ensuring the algorithm processes nodes strictly according to the group size. To begin, let's explore the brute force approach to reversing nodes in K groups. The idea is straightforward: traverse the list to identify groups of K nodes, reverse the pointers within each group, and then reconnect these reversed groups with the rest of the list. While simple in concept, this approach involves multiple passes over the same nodes. For example, one pass is needed to locate each group, and another is required to reverse the nodes within that group. This repeated traversal significantly impacts performance. As a result, the time complexity becomes n squared, in the worst case, where n is the number of nodes in the list. However, since we reverse the nodes in place, the space complexity remains 1. Ultimately, this method, although functional, is inefficient for larger lists due to the repeated operations. Now, to improve efficiency, we turn to the optimized approach. Here, we aim to avoid redundant traversals by combining the processes of group identification and reversal. Using a pointer, we scan the list to count K nodes ahead, ensuring that a full group exists before proceeding. Once a group is identified, we reverse its nodes in place and connect this newly reversed group back to the preceding portion of the list. Afterward, the pointer moves to the next group of K nodes, and the process repeats until the end of the list. The key insight here is that we only visit each node once during traversal, which reduces the time complexity to n. Additionally, since no extra data structures are used, the space complexity remains 1. This method also requires careful attention to edge cases, such as when the total number of nodes is not a multiple of k. By addressing these cases properly, we ensure the structure of the list remains intact. An alternative to this iterative approach is the recursive solution. In this method, we reverse the first k nodes and then recursively process the remainder of the list, with the base case occurring when fewer than k nodes are left. The recursive approach offers an elegant and concise way to solve the problem. By leveraging recursion, it naturally handles the process of breaking the list into smaller sections and reversing each group of k nodes. However, this method comes with its own trade-offs. While the time complexity is still O(n), the space complexity increases to O(n/k) due to the recursion stack. This additional space usage can become problematic for very large lists, as it may lead to stack overflow. For this reason, we opted for the optimized iterative approach as our chosen strategy. It delivers the same O(n) time complexity while maintaining an O(1) space complexity, making it efficient and scalable. Furthermore, the iterative method avoids the risks associated with recursion and is robust enough to handle edge cases cleanly, such as when the list length isn't a perfect multiple of k. Its balance of efficiency, reliability, and minimal resource usage makes it the most practical solution for this problem. When comparing the different methods, we find clear trade-offs. The recursive approach, while elegant, is less suitable for large inputs due to the risk of stack overflow caused by its space requirements. On the other hand, the brute force method is conceptually simple but highly inefficient for larger lists because of its repeated traversals, which increase time complexity unnecessarily. The optimized iterative approach, however, strikes the perfect balance. It is efficient, with a linear time complexity, and uses constant space, making it well suited for handling large datasets. Additionally, it effectively manages edge cases, such as when k equals 1 or when the list length is not divisible by k overall. This approach combines simplicity, efficiency, and robustness, making it the best choice for solving the problem reliably and effectively. To solve the problem of reversing nodes in a linked list in groups of k, we begin by clarifying the requirements. The input is a singly linked list and an integer k. The output is a modified linked list where every group of k nodes is reversed, but groups with fewer than k nodes remain unchanged. For example, if k is greater than the total number of nodes, no reversal occurs. Next, we initialize the necessary components. A dummy node is created and linked to the head of the list. This dummy node helps simplify edge cases like reversing the first group. We also use a pointer called prev_group_n to track the end of the last reversed group, and another pointer current to traverse the list. These setup steps ensure we can efficiently handle node manipulation as we process the list in groups of k. The traversal of the list begins by ensuring there are at least k nodes available for reversal. This is done using a pointer, group_end, which identifies the kth node starting from the current position. If fewer than k nodes remain, meaning group_end becomes null, the loop is terminated. Once a group is identified, the next step is to reverse the nodes within that group. To do this, we first store the node following the kth node, referred to as next_group, so we can reconnect it later. The actual reversal of the group is performed in place using two pointers, previous, initialized to null, and cur, which starts at the current group's first node. By iterating through the group, we adjust the next pointers of each node to reverse their order. This process is efficient and operates in constant space. After reversing the group, we reconnect it to the rest of the list. The start of the reversed group, which is now the kth node, is linked to the end of the previous group using prev_group_n.next. The original start of the group, now the end of the reversed group, is connected to next_group. Then, prev_group_end is updated to point to the end of the newly reversed group, and the current pointer is moved to the start of the next group. This process repeats for each group of k nodes. Key insights include handling edge cases such as when k equals 1, in which no reversal occurs, or when the list is empty, which requires no processing. Additionally, the use of a dummy node simplifies the logic for edge cases, particularly for the first group. This approach ensures a clean and consistent implementation. The provided pseudocode summarizes the steps clearly. First, we initialize the dummy node in pointers for traversal. The while loop continues as long as groups of k nodes can be found, with group_n determining the boundary of each group. When reversing the group, the next _group pointer ensures we preserve the link to the rest of the list. The in-place reversal is achieved by iterating through the nodes and adjusting their next pointers. Once reversed, the group is reconnected, and the traversal pointers are updated for the next iteration. Finally, when all groups are processed, we return dummy.next, which points to the head of the modified list. This algorithm runs in O(n) time since each node is visited once and uses O(1) space, making it efficient and well-suited for large linked lists. To solve the problem of reversing nodes in k-sized groups, we first define a list node class to represent each node in the linked list. This class has two attributes, val for the node's value and next to point to the next node in the list. Then, we define the solution class, which contains the reverse k-group method. This method takes the head of the linked list and the group size k as inputs. Inside this method, we define a helper function called reverse_linked_list to reverse a segment of the list between two nodes, start and end. This function uses 3 pointers, previous to track the previous node, cur to iterate through the segment, and next_temp to temporarily store the next node. By iterating through the segment and adjusting pointers, we reverse the nodes and return the new head of the reversed segment. Next, we create a dummy node with a value of 0 to simplify edge cases, such as reversing the first group in the list. The dummy node points to the head of the input list. We also initialize group_prev to the dummy node, which will help us keep track of the node just before the current group we are reversing. To identify each group, we then use a while loop. Within this loop, we locate the kth node from group_prev by iterating k times. If we reach the end of the list before finding the kth node, the remaining nodes are fewer than k, so we simply return the list without further modifications. If the kth node is found, we proceed with reversing the current group of k nodes. We first set group_next to kth_node.next, which represents the node immediately following the group to be reversed. Then, we determine the start and end of the group by setting start to group_prev.next and end to kth_node.next. Using the reverse_linked_list helper function, we reverse the nodes in this group, passing start and end as arguments. After reversing, we reconnect the reversed group back to the main list. We do this by setting group_prev.next to kth_node, which is now the new head of the reversed group, and start.next to group_next, ensuring that the reversed group links to the remainder of the list. Finally, we move group_prev to the end of the reversed group, which is now represented by start, preparing for the next iteration of the while loop. This process repeats until there are no more complete groups of k nodes to reverse. Here, we start by defining the Java class for the solution. Inside the class, we have a nested static class called listNode, which represents a node in a singly linked list. Each node has an integer value, val, and a reference to the next node, next. We provide 3 constructors, a default constructor, one to initialize the value of the node, and another to initialize both the value and the next node. Next, we define the method reverseKgroup, which takes the head of the linked list and an integer k as parameters. This method will reverse the list in groups of k nodes. To handle edge cases, we include a base condition where if the head is null or k is less than or equal to 1, we simply return the head as there's nothing to reverse. To simplify further operations, especially at the start of the list, we create a dummy node with a value of 0 and point its next to the head of the given linked list. Now, we introduce a pointer, group_prev, which initially points to the dummy node. This pointer helps us keep track of the node before the current group being processed. Inside a while loop, we first locate the kth node in the current group using a helper method, getKthNode. If the kth node is null, it means there are fewer than k nodes remaining, and we break out of the loop as no further reversal is necessary. Otherwise, we store the next node after the kth node in groupNext, which marks the start of the next group. To reverse the current group, we use 2 pointers, previous, initialized to groupNext, and cur, pointing to the first node in the group. As we iterate, we reverse the pointers for each node in the group by updating their next references. When the reversal is complete, we reconnect the reversed group to the surrounding nodes in the list. The node that was previously the first in the group, group prev.next becomes the new group prev, and we continue to the next group. Finally, once all groups have been processed, we return the new head of the list, which is accessible through dummy.next. To support the main reversal logic, we define the getKTHNode helper method. This method takes a starting node, cur, and an integer k, and moves k steps forward in the list. If it reaches the end of the list before completing k steps, it returns null, indicating that there are fewer than k nodes left. Otherwise, it returns the kth node. This helper method is crucial for determining the boundaries of each group and ensuring that we only reverse complete groups of k nodes. The goal of this problem is to reverse every group of k nodes in a linked list. If the remaining nodes at the end of the list are fewer than k, they are left as is. To solve this, we'll use an iterative approach, leveraging a helper function to reverse sublists of the linked list. In our first example, the input is a linked list 1-2-3-4-5 with k equals 2. The desired output is 2, 1, 4, 3, 5. To simplify edge cases, we start by adding a dummy node at the beginning of the list, so it becomes dummy-1-2-3-4-5. A pointer, group_prev, is initialized to point to the dummy node. The first step in the process is to locate the kth node in the list, which marks the end of the current group to be reversed. Starting from group_prev, we move k steps forward to find the kth node. In this case, the kth node is 2, and the node after it, group_next, is 3. Once the kth node has been identified, the next step is to reverse the group of nodes between group_prev.next and group_next. To do this, we call the helper function reverse_linked_list with the start node as 1 and the end node as 3. Inside the function, we reverse the links in the sublist 1-2. Initially, previous is set to none, and cur points to 1. We update the links iteratively. First, cur.next is set to previous, making 1 point to none. Then, previous is updated to 1, and cur moves to 2. This process repeats for the next node, resulting in 2-1. After the reversal, the function returns previous, which now points to the head of the reversed group, 2. After reversing, we reconnect the reversed group to the rest of the list. Group_prev.next is updated to point to the new head of the reversed group, 2, and start.next is set to group_next, connecting 1 to 3. Finally, we update group_prev to point to the start node, which is now 1, and move on to the next group. Repeating this process, the next group 3-4 is reversed, resulting in the final list, dummy-2-1-4-3-5. The output is 2, 1, 4, 3, 5. In the second example, the input linked list is 1-2-3-4-5 with k equals 3. The goal is to reverse every group of 3 nodes, resulting in an output of 3, 2, 1, 4, 5. As before, we add a dummy node to the list, making it dummy-1-2-3-4-5, and initialize group_prev to point to the dummy. The first step is to locate the kth node for the group. Moving k equals 3 steps forward from group_prev, we find that the kth node is 3, and the node after it, group_next, is 4. Now, we reverse the group of nodes between group_prev.next and group_next. The helper function reverse_linked_list is called with start equals 1 and end equals 4. Inside the function, the links between 1, 2, and 3 are reversed to create the sublist 3-2-1. The function then returns 3, which is the new head of the reversed group. After reversing the group, the connections are updated to reflect the changes. Group_prev.next is set to the new head of the reversed group, 3, and start.next is updated to point to group_next, connecting 1 to 4. This ensures that the reversed group is properly linked back to the rest of the list. Finally, group_prev is updated to point to 1, the last node in the reversed group, preparing it for the next iteration. At this stage, the remaining nodes in the list are 4-5. Since there are fewer than k equals 3 nodes left, they are not reversed and remain unchanged. The result for this example is 3, 2, 1, 4, 5. This demonstrates how the algorithm effectively handles groups of k nodes while leaving smaller remaining groups intact. In the third example, the input linked list is 1-2-3, and k equals 4. Since the total number of nodes in the list is less than k, no groups can be formed for reversal. As usual, a dummy node is added, making the list dummy-1-2-3. The algorithm begins by trying to locate the kth node, moving k equals 4 steps forward from the initial group_pref position. However, because there are only 3 nodes in the list, the traversal stops before reaching the kth node, and kth_node becomes none. With fewer than k nodes available, the algorithm simply returns the original list. The output for this example remains 1, 2, 3, which highlights how the algorithm gracefully handles cases where the list size is smaller than k. To summarize, this approach reverses each group of k nodes in a linked list using a helper function to reverse sublists. Key pointers like group_prev and kth_node are used to track the start and end of each group. If the remaining nodes in the list are fewer than k, they are left unchanged. Looking at the final outputs for the examples, example 1 results in 2, 1, 4, 3, 5, example 2 gives 3, 2, 1, 4, 5, and example 3 outputs 1, 2, 3. This algorithm ensures an efficient and systematic reversal of nodes in groups of k while handling edge cases effectively. To analyze the time complexity of our solution, let's break it down into 3 key operations. First, we consider finding the kth node in each group. Each iteration of the outer while loop involves traversing k nodes to locate the kth node, which takes k time. With a total of n nodes in the list in groups of size k, the number of iterations is approximately n divided by k. This means the total time spent on this step is the product of the number of iterations and the time per iteration, resulting in n/k, *k, which simplifies to n. Next, we have the reversal of k nodes in each group. The reverse_linked_list function processes k nodes per group, updating their pointers in k time. Since there are n/k groups, the total time spent on this step is also n/k, *k, or n. Lastly, connecting the reversed groups back into the list requires updating pointers, an operation that takes 1 time per group. With n/k groups, this contributes n/k, *1, which simplifies to n. When we combine these steps, finding the kth node, reversing k nodes, and reconnecting the groups, we see that the overall time complexity is dominated by the traversal and reversal operations. Both of these contribute n, so the total time complexity of the solution is n. Now, let's analyze the space complexity. The reverse_linked_list function uses a constant amount of extra space for pointers like previous, cur, and next_temp. No additional data structures are introduced, so the auxiliary space usage is 1. Furthermore, this implementation does not involve any recursion, so there is no extra stack space consumed. Lastly, the function operates entirely on the input list without creating new list node objects, confirming that the space complexity remains 1. To put this into perspective, let's compare our optimized approach with a naive solution. A naive method might involve creating new linked lists for each group of k nodes, reversing those groups, and then combining them into a final result. While this approach would still traverse each node once, resulting in n time complexity, it would require n additional space to store the new lists. In contrast, our current optimized solution performs in-place reversals using a constant amount of memory, making it far more efficient in terms of space usage. This improvement highlights the advantage of the optimized approach, which achieves the same time complexity but with significantly reduced memory overhead. Now, let's examine how the algorithm performs under different scenarios. In the best case, n is a perfect multiple of k, meaning all groups are of size k. Here, every node is processed exactly once, and the time complexity is n. In the worst case, n is not a multiple of k, leaving a smaller group of nodes at the end that cannot be reversed. However, this does not affect the overall complexity, which remains n. The average case behaves similarly, as the algorithm consistently processes nodes in groups of k and stops when fewer than k nodes remain. To reinforce this, we can mathematically prove the time complexity. Each node in the list is visited twice, once during the traversal to locate the kth node and once during the reversal process. This results in 2*n, which simplifies to n. Additionally, since the algorithm uses a fixed number of pointers and does not allocate extra memory, the space complexity stays constant at O(1). To summarize, the time complexity of the solution is O(n), as each node is visited a limited number of times during traversal and reversal. The space complexity is O(1), thanks to the in-place operations that avoid allocating extra memory. This optimized approach not only achieves linear time complexity but is also significantly more memory efficient compared to naive methods that rely on additional space for reversed groups. By balancing time and space efficiency, this solution provides a robust and scalable way to reverse nodes in k-sized groups within a linked list. When working on the reverse nodes in k-group problem, there are several common mistakes to watch out for. First, failing to handle edge cases can trip you up. For example, if the number of nodes in the list is less than k, or if k equals 1, special handling is required to ensure the solution doesn't return incorrect results or crash. Always account for these scenarios explicitly in your code. Next, incorrect pointer updates are another frequent issue. For instance, if you forget to update the previous pointer to point to the tail of the reversed group, it can cause disconnected nodes or even infinite loops. Another mistake to avoid is reversing partial groups when the remaining nodes are fewer than k. This leads to invalid outputs, so always verify that a group has enough nodes before attempting to reverse it. High space complexity is another pitfall. Using extra data structures like arrays or stacks to store nodes might simplify the logic but sacrifices efficiency. Strive for an in-place solution to keep space complexity at O(1). Finally, not tracking the tail of the previous group or the head of the current group properly can cause incorrect relinking of nodes. Ensuring that all pointers are correctly updated during each step is crucial to a successful implementation. Now, let's delve into some insights that can help you tackle this problem more effectively in an interview setting. A key concept to focus on is dividing the linked list into chunks of k nodes and performing operations on these chunks. Whether you use an iterative or recursive approach, it's vital to keep track of the head, tail, and the next group to maintain the list structure correctly. Recognizing the pattern behind this problem is equally important. The idea of working in fixed-size chunks can be applied to other scenarios, such as rotating parts of an array or performing grouped operations on strings. This broader perspective helps you identify connections to similar problems. Interviewers also often evaluate the efficiency of your solution. Aim for an in-place approach that operates with O(1) space complexity and O(n) time complexity, and be prepared to explain how your implementation achieves these benchmarks. Lastly, don't overlook recursive variations. Recursion can provide an elegant way to break the list into groups and reverse them, though you should be ready to discuss the trade-offs, such as increased memory usage due to the recursion stack. Finally, let's explore related problems and alternative approaches to solving this challenge. A strong foundation for this problem starts with mastering reverse linked list, LeetCode problem 206, as it's the building block for reversing k-groups. Another related problem is swap nodes in pairs, problem 24, which is a simpler variation where groups of size 2 are reversed. Rotate list, problem 61, is also conceptually similar, as it involves performing grouped operations on a linked list. Of course, reverse nodes in k-group, problem 25, is the primary focus here, but solving these related problems can deepen your understanding. Now, in terms of alternative approaches, the recursive method involves reversing the first k nodes and then using recursion for the rest of the list. This approach is elegant and intuitive but can lead to stack overflow for very large lists. On the other hand, the iterative two-pointer method is more efficient, as it reverses groups in place with O(1) space complexity, though it's slightly more challenging to implement. Finally, you could use extra space, such as arrays or a stack, to store nodes and reverse groups. This approach simplifies the logic but increases space complexity to O(n), making it less optimal. Carefully weigh these trade-offs to determine the best approach for your specific requirements. Great job completing this problem walkthrough. To summarize, we tackled the challenge of reversing nodes in k-sized groups within a linked list, discussed various approaches, and highlighted key considerations. Remember, practice makes perfect, so keep honing your skills. Thank you for watching, and we'll see you in the next problem breakdown. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!